So some of the stuff I will repeat. So we'll talk about numerical integration today. So just to connect it, where did we end with? So we were working a lot with the Hamiltonian equations of motion, right? That look like this. So this is something you should be now very familiar with. And you also are familiar with that. If I write the z, that actually means x and v, right? But x is positions, v is velocities, just to get in. So this whole thing is our z. And this is the Hamiltonian is sum of the potential function plus the kinetic energy function, which is just velocity squared, right? And we are solving an initial value problem, IVP, which means that z0 is given to us. And our task is to compute zt for all t greater than 0. So the t is a time parameter, right? And ideally, we would find an analytical solution. So really find a function zt, okay, which goes, as I said before, that z is a function that goes from time to phase space to 2n, right? Positions and velocities. This is just kind of warm up to get up to speed where we left off before. So ideally, we would like to find this analytical solution, like an actual function in terms of like sines and cosines and some sort of functions depending on t and possibly some other parameters, such that if you compute a time derivative of that function and plug it into the gradient of the Hamiltonian, this equation is always satisfied at all times, right? That's the analytical solution. That's the holy grail of solving ordinary differential equations. But as you know, that's not always an option, right? It's only possible for very simple potentials, such as for quadratic potentials, which lead to linear forces, which lead to linear ODEs. That's an example where we can analytically integrate it. And there is about like 14 other examples known to the mankind where you can analytically integrate it, but for most practical things, you cannot. So what you need to do is exactly this. What you need to do is numerical integration. And this is the first thing I wanted to clarify, like why this is called integration. Is that kind of clear? Because what integration usually means in 1D, that was pretty ugly, let me try again. So integration usually means that I am given an interval, if I want to compute a definite integral, right? I have some function which lives on that interval, and there is some function like this, right? Then integration usually means computing the area under that function. Sometimes you can also hear the term quadrature. That's like a historical term for integration. It means basically the same thing, okay? But this is slightly different, right? Because that assumes that this function f of x, that's given to you, right? So you know the function, you can evaluate it wherever you want, and your job is to compute the area under the function. That's the definite integral. That's the traditional problem of integration, okay? Now here it's a little bit fishy, right? Because here you don't have that function. So the first thing I wanted to talk about today is why is this even called the numerical integration problem, and how does it actually relate to this traditional view that you are given a function and an interval going from a to b and need to compute the area under the function. That's like the traditional integration thing. Okay, so let's. So the first thing we do is we discretize time. Okay. So I can draw it like this. That will be like my time axis. So this is time, which starts at some t0, which equals 0. And here I exactly know where I am at, right? Those are my initial conditions. So let me denote them as this, z0, okay? And discretizing the time means that I have discrete time steps. So I'll have t1, which will be equal to some h. There will be some t2, which will be 2h. There will be some t3, which will be 3h, you can see the pattern, right? My tk will be k times h, where this h is just a scalar number, and that's my time step, okay? So whenever I discretize, the first ugly thing I have to deal with, I have to pick the step of the discretization. In the case of time discretization, is the time step, okay? And so here I assume that the time step is constant, that between t0 and t1 there is a time of h, and between t1 and t2 there is also a time step of h, and between t2 and 3t the same thing. That doesn't have to be the case. There are also adaptive methods which actually change the size of the step as they progress. They are used, especially in some areas, but they are a little bit more complicated. So we'll focus more on the fixed time step. So meaning you have a single age and you always advance the time by h. There is also, yeah, okay, I'll get to that later. So what we would ideally, so what numerical integration means is that you are given this z0, those are your initial conditions, and what the numerical integration does, it computes this z1, z2, z3, and so on, such that ideally you would have the zk being as close as possible to the true continuous solution at time kh. Okay, so if this z is my function, that would be like the ideal continuous solution, which I usually do not know what that is. Okay, that thing on the right. But what I do know is that I would like my numerical integration approximates the zk to be as close as possible to this. Okay, these things means as close as possible. I'd write they're equal, but requesting that to be equal, that's not realistic. So this means like approximately close to. Okay. All right. So let me clarify why this is called integration. Okay. So let's assume that you already are somewhere, that we already have some z at time, we already are at some step k, okay? We are already somewhere. It could be the very beginning. That kind of doesn't matter. The idea is the same all the time, okay? So if I already have the z of tk, how would I compute the ideal z at tk plus 1, okay? So here I'm talking about the exact solution, okay? So let's, for a little bit, just entertain the theoretical possibility that we can actually evaluate the exact solution, okay? And it's also why I started with these lectures, like studying the continuous case, just to give you an idea, how does it relate to the discrete case, right? The discrete case really is just an approximation of the continuous case, so it's important to understand that one. So let's talk a little bit more about the continuous case. So if we wanted to actually exactly advance from the exact solution at time tk to the exact solution at tk plus 1, how would we do that? And that's what illuminates the term, the numerical integration, or time integration. You can hear it in all sorts of contexts. So let's put some math on this. So let's say, how would I express tk plus 1 in terms of the previous one, in terms of tk? So you can imagine that tk is t0 to make it simpler, but this applies equally wherever you are in this discretization, okay? And there's going to be some plus. And do you know what will be there? Did you guys talk about it the last time, James?
The change in z.
Uh-huh. Yeah. And what do I do with the change in z?
You add it to z at time k, and then that becomes your z at time k plus 1.
That's exactly right. It's changes of z and add them together, yeah. And if you add many infinitely small contributions, how that's called? That's integration, right? So this adding, that's exactly the right intuition to have there. That's right. So mathematically, I can write it like this, as an integral from tk to tk plus 1. So adding the small differences of z, and that's exactly the z dot t, the time derivatives. Okay. So the catch there is, though, that you don't know what this z is. Okay, that you are kind of in the business of computing it. Okay, so that's how it's different to like the regular setup, the traditional integration setup, where you are given the function. Here you are not given the function, you're kind of discovering the function as you go, okay? Or maybe better said, the function is implicitly defined by the Hamilton's equations, okay, by this formula. So I can actually also rewrite this. I can rewrite it like this, as ztk, I'll just copy that term, right? And then this integral, of course, if this satisfies Hamilton's equations, then I can just plug there the right-hand side, right? So I can just plug there this, the gradient of the Hamiltonian of z of t dt, okay? And again, the tricky thing is that you don't know what the zt is. You know what the z is at tk, those are your initial conditions, okay, at time k. But this is still, so this is something you cannot really compute for most Hamiltonians, but it gives you an idea about what does this mean, what does the idea of a time step mean, what does it mean to advance your state from time tk to time tk plus 1, okay? And what does it mean is really is to integrate this function where this z satisfies this formula. And one way you can look at this basically mathematical way of saying take infinitely many, infinitely small time steps, and you will get the exact solution, okay? I guess that's probably the good intuition to have in the back of your mind, right? If you basically, let's say I'm here, that my k is 2, okay? So I want to go from t2 to t3, okay? And what this means basically is saying take infinitely many small, super tiny time steps, okay? And each of them approximate that integral. And as these go to 0, you will be approaching the exact solution, okay? And that's why it's called integration, because you are really evaluating this integral, except that the unknown function is part of that integral, so that makes it a little bit funny. But we can deal with that. All right. So basically, every numerical integrator approximates this. Okay? That's what numerical integration is approximating this term. And why we talk about it is because there are many different numerical integration techniques. Some of them Dimitar presented last week, right? And unfortunately, there is no single integration technique that would just like solve the problem completely. There are just trade-offs to consider. And that's essentially why we are discussing this and why so many methods have been invented. But they all have this one thing in common, that all of them, what they do is approximate this integral. Okay, so every numerical integration technique for a given time step, right? This tk to tk plus 1, there is always the time h elapsed between tk and tk plus 1, because I assume this fixed time step thing. So the other way you can look at a numerical integrator, it's essentially a function which maps, it's a mapping from zk to zk plus 1, okay? Equivalently, and that's how they are usually written, not in terms of the phase-space variable, but in terms of positions and velocities. The positions and velocities at the current time step, like here, they are mapped to the positions and velocities in the next time step, xk plus 1 and vk plus 1, okay? And this little arrow, that means the integrator, the specific numerical integrator you pick, okay? And each of them, this is like the holy grail. That's what they would ideally return. That's what they are trying to approximate. They are trying to get as close as possible to it, okay? So when you read like some standard books about numerical integration, you can sometimes read things about local error and global error, because the numerical integrators are an approximation, right? So inevitably, they are gonna make some error. And it's important to be able to quantify the error. And there are two main error measures. The first one is a local error measure, which essentially is exactly what I just said. It's the difference between what the numerical integrator gives you and this value that would be like the ideal solution, okay? So let me write it in terms of a formula. So the local error is the zk plus 1. That's what the integrator gives you, okay? These things, the z0, z1, z2, z3, the zk's, those are the approximate values, okay? We assume that at the previous step, at z of tk, we had it exact, okay? And we compare to that integral, okay? Exactly this thing over here. I'll just copy that over, okay? So just the j, gradient of the Hamiltonian, z of t dt. And I have some metric, like for example, the Euclidean norm, that's okay, okay? Now the problem is that this I usually cannot evaluate exactly. So one way you can be evaluating an integrator is to run it on a test problem where you actually can evaluate this exactly, where you have an analytical solution. So if you remember still the very first lecture we had, I did this harmonic oscillator example. That was one of the rare examples where you do have the analytical solution, so you can exactly compute this thing, okay? So if you have an integrator, and I guess that's an important point about an integrator, the integrator should work with arbitrary Hamiltonian, or at least with arbitrary potential energy, okay? So the integrator is, think about it as a function which you give the Hamiltonian, and you give it the time step, and you give it the initial conditions, and it computes the approximate solution for the z of ftk plus 1, okay? So the way you can test an integrator, and I think Dimitar did some of this analysis last week, is that you run it on some Hamiltonian where you do have the analytical solution. So then you know what this is exactly, and then you can really evaluate the error the integrator is making, like really compute this as a number. Okay? And if you have then multiple different integrators, then you can compare their errors and pick the better one on these test problems. Okay? So the local error is a good, but a better error is a global one. Actually, what is, let's see if you discussed that the last time, or if you remember that, what is the limitation of the local error? Or like, I guess one of the nasty things of numerical integration, right?
Is it then if you have a large enough local error, you have some overshoot, some instability?
If you have large enough, what you have?
Local error. What's your local error?
If you have large local error, then you have overshoots. That's right. But the problem is that this actually happens over the course of time steps, right? Really?
It accumulates together.
Exactly. It doesn't have to accumulate, but it actually may accumulate, okay? And it's kind of unclear, right? So, but it is clear, right, that the Z0, that's gonna be perfect. Those are the initial conditions. Zero error there, right? Now the integrator makes a little bit of an error in Z1. Hopefully it's small, okay? It can be positive error, it can overshoot it, or it can be negative, it can like undershoot it, or it can be error in whatever directions, right? You cannot always clearly tell whether overshooting or undershooting, but there will be some error on Z1, okay? And then what the integrator does, it takes the Z1, because that's the best thing it can take. It doesn't have the exact solution at time h anymore, at time t1, okay? So it already starts with a little bit of an error, and then it's run again. Then it produces Z2, and if I'm unlucky, there is another, there's gonna be another error between Z1 and Z2, okay? And there's gonna be another error between Z2 and Z3, okay? And this local error exactly quantifies this error made in one step, okay? But the worry is, what if I am so unlucky that these errors actually accumulate, okay? That's a pessimistic viewpoint. There's also an optimistic viewpoint, which says that maybe sometimes I will overshoot the error, sometimes I will undershoot. So on average, during the course of many time steps, the error will actually average away. That's an optimistic view, okay? And we will see that this optimism and pessimism has a lot to do with symplecticity, what I talked about 2 weeks ago. But we'll get to that later. But just the concern that this error may accumulate, that's what leads to a global error measure. And so the local error does not account for the accumulation over the course of multiple time steps. Okay, the global error does, and the global error is really simple to write and really hard to compute. The global error is simply what the discrete integrator gives you, the zk, minus the exact solution of z of tk, okay, in whatever metric, let's say Euclidean metric, okay? So that assumes that you know what the exact solution is, right? So that's hard. There are some, in numerical analysis, there are some ways you can compute it using like exponential, but then these bounds get kind of pretty conservative. So this is not always a useful thing to work with. That would be the ideal thing you would look at, but it's not always practical. So usually you just look at the local error. All right, so as we said, every numerical integrator, every numerical integrator is a mapping from the current state or from the initial conditions to the next one after time h elapsed. Okay, and there are many different methods. I guess they can be kind of simple, explicit methods, which is means that the mapping is given to you by closed form formulas. Essentially, a recipe: compute this, compute that, right? You had the example of the forward Euler integrator. I will redo that because that's an important one, or the Runge-Kutta methods, right? And many other methods, including some symplectic methods, are examples of this category of explicit integrators, meaning you're given closed form expressions for computing zk plus 1 from zk. Okay, and then there are implicit methods, which you guys also discussed last week, right? Is that right? Like the most well-known is implicit Euler or backward Euler. It's the same thing. And that's a little bit trickier. That means that you are not given a closed form formulas, but you are given typically a system of nonlinear equations which you have to solve. Okay, so you are no longer given an algorithm, but you are given a problem which you have to solve. And once you have solved it, you obtain the xk plus 1 and bk plus 1. All right. So let's actually look one more time at forward Euler, because that's the most obvious method. And one thing I would like to do today is to do a graphical comparison of the numerical integrators. Yes, yours, Jing. She created really nice images for our previous paper, and it's a really nice way to appreciate the similarities and differences of different numerical schemes. So let's quickly take a look. How do we actually apply this theory to get the simplest possible integrator? And that's forward Euler. Actually, can you just say just by looking at this? So we said that every numerical integrator is going to be approximating this integral, right? What's the simplest possible way of approximating that integral? It's the same question as what is the forward Euler method? So think about, again, like integral, think about it again this way, right? That you are given like a function, some funny function. Looks like this. And you need to estimate the area under the function, right? That's what integral is, right? And that's also what people usually refer to as quadrature rule, when you're approximating that integral somehow. What's the simplest possible approximation of this integral you can make? Assume that this h is like really small. Helps. Or look at this picture, okay? If I have some function, maybe this will help. I don't know what that function is, but what I do know, I know what the function is at this point here, okay? Look at the upper left corner. I know what the function is there, right? That's my initial condition. That's why I'm starting, okay? That's my z at tk. That I know. Or maybe Trevor?
Oh, no,
Okay,
yeah,
just...
you just construct a trapezoid. You predict the next point from the slope, and then just the area of the trapezoid.
So yes, so trapezoid actually leads to already a slightly more advanced numerical integration thing. So you're right, the trapezoidal rule would be that's what leads to very useful numerical integrators.
So in other words, you pick a time step and you multiply whatever your value is at the time step, and then you have a rectangle.
That's exactly right, yeah. So if I was to draw this idea on that figure, you know what is this, right? And you make this approximation. You say, oh, maybe the function is just constant there, okay? And then you just multiply this value by h. You know this is your time step h, right? So multiply this by h. So you return this area, okay? And if you were lucky and this function was not too wiggly, or in other words, if your time step was sufficiently small, then this is going to be a good approximation. Okay, so let's put this again in terms of math, and actually let's derive it even from the Hamiltonian equations to sort of connect it to what I was talking about before. So again, real quick, let's recall ourselves what the terms were. So the gradient of the Hamiltonian, this is something I hope you remember, that's the gradient of the potential and v, right? Which I can also write this as minus forces at x. I guess that should be also some x thing here, and then there is v, okay? And then the J matrix is our 0I minus I0 matrix, right? So I'm writing it out to rederive what this J gradient of the Hamiltonian was, and that's just the matrix multiplication of those things. So that's a V and F of X, okay? But the force is a position-dependent function, so I write it as S of X, so that's my force function. Or, so I just write the F so I don't have to write minus gradient of E, okay? And also because this is usually written in terms of forces, okay? So let's now write this thing in terms of positions and velocities, okay? So I will write it like this. So I'm looking for xk plus 1, vk plus 1. That's what I gotta compute. That's what a numerical integrator needs to compute. I know xk and vk, okay? At k equals 0, those are my initial conditions. If I'm at k equal, I don't know, 15, then I assume I've already computed 15 steps. So I already know what that is. There might be an error, but that's what it is. You just assume that's where we are. We just go from there, okay? And now there is the integral from tk to tk plus 1. And that's the gradient of this thing, right? The J matrix times the gradient of the Hamiltonian. What did I say? Did I say it's the integral of this thing? So that's an integral of, let me write it like this, of Vt and f of x of t, okay? And that's integrated over time, of course. Okay, so the v and the x are functions of time which I do not know. I only know them at tk. Okay, but as I said, as you said, we can approximate it by a simple quadrature rule, right? And the simplest quadrature rule would be to say, let's replace this integral with the value of tk and multiply it by the time step h. That's the difference between tk plus 1 and tk. Okay. So if I do this, so that's the simplest possible quadrature rule you can use. So that means replace this with h times vk, and replace the other thing with h times f of xk. Okay, that's the values of the functions that were there at time tk. And those I know. That's easy. I just grabbed that. Those are my initial conditions. And of course, if I add it together, then it's xk plus hvk, and this is vk plus hf of xk. All right. I could also, if you want, you can also write as minus gradient of the potential. Okay, it's exactly the same thing. So if I'm just to put it together, then you will get the usual forward Euler integration rules, which look exactly like this. And vk plus 1 is vk plus h of f at xk. All right, so this is what you had the last time, right? I just wanted to connect it to the Hamilton equations and to the integration so you can see how does it play. This is really the simplest possible approximation of this integral you can make, okay? So this is the forward Euler method. And I believe you also discussed last week that this method is very, any questions on this? Is it clear? So this is the most obvious method and the most logical, I think, but it's also probably the worst possible method you can pick, right? It has probably the worst stability properties, and it doesn't really conserve anything but linear momentum. I'll talk about that later. So this method actually works really bad. I will not go into details on that because I believe you discussed that last week, right? How terribly that can fail. Now, it will be actually fine if the time step h is small enough, okay? All problems of numerical integration can be cured by lowering the time step. The problem is that you don't know how small the time step needs to be, and that depends. That depends on what exactly is in this f function or what exactly is in this potential function, okay? But in theory, you can always fix all the problems by taking smaller h. The problem is that you will, of course, pay for it by compute, right? Because if you take a time step of like 1 microsecond, and you need to actually advance your animation by 30 milliseconds or so on, then you will actually have to pay with a lot of compute for tiny time steps. I'll talk more about that later. So this was the, oops, that's not what I wanted. So this was the simplest possible method, that's forward Euler. It's an example of an explicit method, of course, because this is just very straightforward computation, okay? But because the forward Euler doesn't really work all that well, many other methods were invented. One of them is the implicit or backward Euler. And do you remember what the key idea there was? It uses kind of like a weird approximation of that integral. At first weird, eventually it kind of makes sense if you think about it. So how do you get the forward Euler instead of the backward Euler? Or how would you get it on this? Think about it in terms of this figure, okay? Here there was, I'll make the figure bigger because it got a little bit ugly now. So here is my tk, that's where I am. This is tk plus 1, that's where I want to get. This is what this is zk, right? This is what I know what it is. And this is my zk plus 1, that's what I don't know what it is. And what I'm trying to do is I'm trying to compute this integral. So the forward Euler corresponded to saying, hey, I know the value here, right? Let's just extend it and integrate, okay? So what is implicit Euler on the same figure? Well, it's backward Euler there.
I would assume you just go backwards and take the rectangular constant from the ending point.
That's exactly right, yes. You do it exactly in reverse. You say, hey, let's say I know the value here. Now the tricky thing is you actually don't know the value there. But that's actually okay. That's like the mathematical way of thinking, like, let's take the value here. Nobody cares that you haven't computed it, okay? That's the difference between mathematics and computing. It exists, okay? And mathematician is like satisfied, right? Because there are these theorems that the solution exists, so certainly the value will exist, so you can grab it, right? How do you compute it? That's not their business. But you can still entertain. This idea actually works. It leads to a very useful method, right? So you take the value here, you extend it exactly the same way. You just multiply it by h, and then say, hey, this is now my approximation for that integral, okay? So the derivation would follow exactly the same pattern, except that here, when I'm replacing this integral with like some value multiplied by h, here I actually would put there vk plus 1 and xk plus 1 here, all right? Which means that I would get vk plus 1 here and xk plus 1 there. So the formulas I would get are looking like this. So that's xk plus 1 equals xk plus h vk plus 1. That's the trick. And vk plus 1 equals vk plus h of f of xk plus 1. Okay? So I will highlight this. This is what forward Euler uses. This is what backward Euler uses. Okay? And indeed, there is a problem because xk plus 1 and vk plus 1, that's what I'm computing. I don't know what that is. I know what xk is. I know what vk is. I certainly know what h is. And I can certainly compute the forces at xk. I have the force function or the potential function equivalently. But I don't know what xk plus 1 and vk plus 1 is going to be, right? Did you guys talk about it the last time? How do you solve this? Okay, and we won't go into how today either, because that's an entire probably an entire separate lecture. But what it is algebraically, this is a system of equations. Okay, and if f is not a linear function, which it usually is not, that's a system of nonlinear equations. Okay, like imagine this f is some like, I don't know, sine x or x cubed or some. That's what it usually is, some kind of polynomials in like realistic elastic models. But it's a system of equations which you can solve using some numerical methods. Okay, and if you solve it, you actually get the xk plus 1 and vk plus 1, and that's the result of that integrator. Okay. All right, and then there is million other techniques, and some of them I will. Some of them I will discuss today, and most of them I won't because there is so many techniques that it's not even funny. There's an entire zoo of numerical integrators. This is the forward Euler and backward Euler. This is really just the tip of the iceberg. But let me give you like a little bit of a perspective of actually how this differs from scientific computing. Okay, so. Physics-based animation, phys-based anim, versus kind of the computing view, or scientific computing, that's how it's often called, or applied math kind of view. So the traditional like scientific computing kind of view is that what your goal, there are different goals, that's really the thing. Okay? The goal of computing is that you actually want to approximate the continuous solution accurately enough. Okay? Ideally, you would be able to put a bound on the global error. Like ideally, you would say, so in the computing, what you would ideally want would be to put a bound on this, on the global error, and have some epsilon. And your integrator would be able to guarantee that that error won't get above some epsilon. And the epsilon would be like your tolerance thing, right? You know that every computer is doing rounding errors anyway, right? So you will not get exactly the right solution no matter what. So you might as well say, okay, I'll pick some epsilon and I will get the solution up to epsilon, right? And that's the best you can do, and that's what you do if you like want to do like predictive simulations, like if you want to simulate like a flow of an air around an airplane, or some like really serious things, or analyze stresses in like a hip replacement kind of thing, that you really want to like, you want to be sure that you are computing the right thing as accurately as you can. And this typically leads to some higher order methods like RK4, and those are explicit methods of higher order. What the order means, I think you discussed that last time too, so just briefly, all this stuff is first order, that I just take first order derivatives and just multiply by h, but you can also do second order approximations. Basically, don't say I just replace it by a line, but I replace it by some higher order polynomial, and that gives me higher order methods. That's the gist of it. So these guys usually use some higher order methods, and they do error control. Okay? The error control means that they have some mechanism to estimate this local error. Again, it's almost impossible to compute it exactly, but there are ways to estimate the local error, and that's how it's usually done in computing. Okay? How do you estimate the local error? There are many ways to do that. The easiest probably would be to try to do 2 time steps of h half. Okay? Divide your time step by half, do 2 of them, with the same integration method, and compare the results and see if they are similar or different. If they are very similar, then you can be kind of confident that your time step h is not too bad, right? If they're very different, then you're like, oh, maybe I need to take a smaller time step, okay? And that's what this local error control is usually used for, is for adapting the time step, okay? So adaptive time stepping, adaptive time step. It's essentially a way of quality control. If the time step is too large, then the integrator is not giving you accurate enough results, and your defense against this is to lower the time step. And then when things get better again, then you can try to increase the time step again, so you are not wasting compute unnecessarily. Okay? There are some more advanced methods. There are sometimes like a pairs of higher order integrators, so there's like a pair of RK4 and RK5. One of the go-to methods, which is usually recommended in the context here in MATLAB, is ODE45 or ODE45S or something like this. And that's exactly this kind of idea, that it uses one method, RK4, for the main integration, and RK5, so a higher order, a little bit more accurate method to estimate the error, for error control, and for adapting the time step. Okay? So if you ever want to use something like this, then just all you need to remember is ODE45 in MATLAB. That's one of the things that was found through many tests of time. That's like a good way of doing this. If you really have that goal, that you would like to get an accurate solution of your ordinary differential equation. And what this usually leads to is a lot of compute. Okay, even with higher order methods, you usually end up using pretty small time step with like practical problems. Okay, because practical problems are kind of nasty, and these forces can be pretty large, and that really forces you to take a small time step even with higher order methods. And that means that so you advance for like a reasonable time, even like a second, then you actually need to do lots of computation. Also, there is, by the way, there is no single answer on what is the right time step. That entirely depends on the application. Okay, if you are doing molecular dynamics, your time steps are going to be totally different than if you are doing climate predictions, where time steps might be years. Okay, so that's entirely application dependent.
Does it also apply to the epsilon that you choose?
Absolutely. Yep. That depends. Yeah, totally. So there you need to know a little bit about your problem to choose these things. And what does this usually lead to is basically lots of compute, and also typically this is compounded with the problem that you want lots of degrees of freedom. That this n thing, or the 2n, the dimension of the phase space, is like really high. They were like ideally like have as high resolution simulations as possible. So that usually leads to supercomputing. So you do lots of compute in parallel. It's a little bit cursed here though, because you can see the sequentiality of this process, right? To be able to compute the next time step, you must have computed the previous one, okay? And there are some methods that try to deal with this, parallel in time methods, but they have lots of problems, so I haven't seen them being widely used, even though there is a community around it and people are trying to parallelize it in time, but it's hard, as you can see, because it's like inherently a sequential process. Okay, so what people in computing are usually in the business of is speeding up this one time step to make that fast using parallel computing. So this was kind of an aside, because in physics-based animation we have a different goal. Okay, in physics-based animation we are in business of producing an animation. Okay, so that's how it connects to computer graphics. Okay, so physics-based animation. What is an animation? Animation means a sequence of images which are spaced nicely in time, that when you play them one by one, it looks like a moving thing, right? And it's a well-known thing that for humans to perceive the motion as smooth, what you need is at least 24 frames per second, right? Your usual standard is 30 frames per second, but now they're like high frequency displays and standards, so it's not uncommon to have 60 or even 120 frames per second. But it's already like considered luxury kind of thing. The 30, you already see a very, very smooth motion, right? So what animation is, I can draw like a similar figure. I have a time axis, right? And I have frame. The frame is an image, okay, with something on it. And there is another frame. There is another frame here. There's another frame there, okay? Frames. And frame by frame, I mean an image, really, which you then put on the screen one by one, and that creates the illusion of a smooth motion. That's what physics-based animation is about, right? And just by the similarity of these figures, you can see that it's very similar to numerical integration, right? So in physics-based animation, ideally, if you are creating the animation by solving an ODE, ideally you would set this time step h to be exactly the same as the frame rate, right? Which in most cases is 1/30th of a second, which is roughly 33 milliseconds. That would be the ideal time step you would want to take, okay? And the other interesting difference is that you are actually usually not trying to simulate the real world, okay? In like scientific computing, if you are like simulating the forces acting on a wing of an airplane, you better get those forces right, because if you got them wrong, then it breaks down. That's gonna be a problem, right? But the way you evaluate an animation is by looking at it. If it looks good, then it's a good animation, right? And it's kind of like an aesthetic kind of thing, and sometimes it's not you evaluating it, but it's like your audience or the director of a movie or some like artist evaluating that animation. But that's really the metric. So in physics-based animation, people call it visual plausibility or physical plausibility. The result does not necessarily have to be physically realistic. You don't have to have the forces and positions and velocities computed to any given level of accuracy. It just needs to look right, okay? And that's, of course, a loose term, right? How can we like connect it to the mathematics and the things we discussed about? How do you quantify the plausibility, right? Well, you cannot directly quantify unless you simulate the brain and all that's going on in the brain. Then you cannot directly quantify the plausibility. But actually, it turns out that we can at least approximate it using some of the tools we discussed before, using the motion invariance, okay? Which is motivated by the fact that maybe we can at least defend against implausibility of an animation. So if something is going terribly wrong, you can capture that mathematically, okay? So I'd like to point a connection or like a proxy for visual plausibility would be the motion invariance we discussed in the first few lectures, okay? What motion invariance did we discuss exactly? Let's quickly recap that. There are some quantities that are conserved in the continuous solution of the motion, meaning in the perfect solution of the motion. And if there is something implausible, you can often relate it to violation of some of these motion invariants. So what were the motion invariants? The things that are conserved during the course of a motion. Or some things the continuous solution always satisfies. I guess this is the other way you can look at it. It's actually how it was historically developed. That when people found out that the analytical solutions are not going to happen after trying really hard, they at least found that you can find at least some properties of the analytical solution, of the exact solution, without actually having to solve it. So something that's actually doable. Those are exactly the motion invariants, right? So we had the energy conservation or Hamiltonian conservation, that was one of them. Then there was momentum conservation. And we talked about different types of momenta, right? There are different types of linear momenta and angular momenta. And the third thing was symplecticity, which is a slightly different type of invariant. It's not with respect to time, but it's with respect to varying the initial conditions, okay? Nevertheless, it's maybe the most important invariant for numerical integration, okay? So all of these things are exactly satisfied in the continuous solution, continuously. Okay. And the thing is that some numerical integrators satisfy them discretely. Okay. Meaning that some numerical integrators exactly preserve these properties. Okay. And that's what often can be linked to visual plausibility. Like, for example, the instabilities of forward Euler, which you talked about last week, can be diagnosed as violation of energy conservation. The energy should have been conserved. What forward Euler does, it actually explodes the energy. If you look at the plot of the energy, it just grows above any bounds. And that's a way you can explain why it works so bad. And then you can say, okay, maybe if I actually request my integrator to be energy conserving, then this cannot happen, right? So that's a way you can kind of request at least some of the plausibility, okay? So what does it mean satisfying these properties discretely? So for energy and momentum conservation, both of these things are, so these two things, those are the first integrals, right? That's the formalism of first integrals. And they are satisfied in discretely or conserved discretely. So if f is a first integral, but you know in the continuous world, the f of z of t would be constant, right? That would be that's the continuous view. And in the discrete view, well, that's the same thing. You say that fzk is constant, or you can just say that's equivalent to saying that the f of zk plus 1 is equal to f of zk, okay? Meaning the numerical integrator produces zk plus 1 such that after I evaluate the first integral, it's the same as it was before. And the first integral can be energy, the Hamiltonian, the total energy, aka the Hamiltonian. It can be a linear momenta, it can be angular momenta. Okay? And it turns out that some numerical integrators do have this property and some don't. And you probably want to pick those that do, because then they are less likely to give you implausible solutions. Okay? Symplecticity is slightly different. Symplecticity is not a first integral. Okay? So we say that an integrator. So integrator, I hope now that's clear. That's a mapping. Let me call it mapping ZH, and it's a mapping from phase space to phase space. Is that clear now? If I write, that's essentially like a formal way of saying what I was saying before, that the integrator is a mapping from phase space to phase space, from initial conditions to the state after time h, where h is the time step. Okay, so this is maybe let me be really explicit and say this is a numerical integrator. That's a mapping. Okay, and we say that the numerical integrator is symplectic if this function ZH is a symplectomorphism. Symplectomorphism is a special case of diffeomorphism. Those of you who do medical imaging heard about diffeomorphisms. What is diffeomorphism? That's a smooth mapping, which is a bijection, and its inverse is differentiable. Symplectomorphism is a special case of diffeomorphism, so it needs to be a diffeomorphism which satisfies this additional constraint. That's the one what we had before when we talked about it in the continuous case, that this equality is true for every Z0, okay? For every Z0 from the phase space.
You see? Diffeomorphism? Diffeomorphism? You said symplectomorphism is a special case of what?
Okay, I'll write it. Diffeomorphism, which satisfies.
So it's DIFROM. You're spelling that DIFROM, DIFEOM.
Oh, how's it? Maybe I spelled it wrong. That's.
I just never heard of that term before. I just wanted
Oh yeah,
to be
okay.
able to
I might have the spelling wrong, so let's just Google it real quick. There's double F's, yeah,
Okay.
sorry.
So that is a D. Okay.
Diffeomorphism.
Diffeomorphism.
And it's just a math way of saying that this mapping is nice enough.
Okay.
Then the main thing is it's a bijection, so it's invertible and it's also differentially invertible. Maybe more practical is the intuitive explanation of it. If you look at this mapping as a deformation, which it really is, it's a mapping from 2n to. You know what? I will illustrate this graphically in just a little bit, and that will hopefully clarify this what is for now kind of abstract stuff. Yeah, let me just do that. Let's look at what this all means in a 1D example that Jing is very familiar with because she basically did it with the potential of 128 x to the power of 4, okay, mass 1 as we always assume, and the time step of 0.4 seconds, okay? So let's look at what these things mean in this 1D toy case, okay? So in this case, any numerical integrator will be a mapping from R2 to R2, right? Because then it's 1. So that means that I can visualize it beautifully using image deformation, right? Because in R2 I can draw some image and I can look how that image distorts by that integrator, okay? So let's take a look at it because it's quite cool. That's not what I meant. To do this. All right. So again, the credit for that image goes to Jing because she crafted this thing. So this is my visualization of the initial conditions. Okay, so this is my phase space. So this is initial conditions. Is it big enough, or shall I make it larger so you can see what's going? I guess on the screen it's kind of small, right? So let's see if I can make that a little bit bigger. Better?
That's great.
Okay, perfect. So this is initial conditions. Visualization, really, of initial conditions, okay? You can see this is the x, that's the positions, this is the v, velocities. There is just a single degree of freedom. So it's essentially a harmonic oscillator, except that it's not the standard harmonic oscillator. It's a harmonic oscillator with this potential, 128 x to the power of 4, which is something what we pick to get nice images, okay? If you, by the way, if you get there x to the power of 2, you would just get the rotation, which has analytical solution, so that would not be that interesting. But here we actually already get an interesting motion, okay? So the idea is I can pick any point here, and I can say that's my initial x and v, okay? And I will simulate this motion for 0.4 milliseconds, okay? So I'll simulate 0.4 seconds worth of motion, 400 milliseconds, okay? And every point there maps somewhere, okay, onto the phase space. This maps somewhere else. For every point, I can compute the map, so I can look at this as image deformation, okay? And if I show you the exact solution, that looks like this. So I can first compute it for the exact solution, okay? Jing, do you wanna, while I look it up, do you wanna explain how did we compute the exact solution? Because it's not quite exact.
Yeah, so we use a very small time step, like 1,000th of the 0.4 second, so it's 0.4 millisecond, and do it like 1,000 times.
Exactly, yeah. So the way you compute really accurate solution is by taking tiny time step, okay? So if I need to simulate 0.4 seconds, just as Jing said, what we did, we took like a really tiny time step, like 1 millisecond or something like this, and we just run 4,000 of them or 400 of them, or even more actually, and smaller ones. And if you do this, you get a pretty accurate solution. I could also draw the axes here, right? If you this is still the same phase space, okay? So this is still my x, and this is still my v. And this kind of tells you where the mapping goes, right? So this point here in the middle of the fish is mapping over here, okay? And so on for all the points. So that's what the motion, that's how the exact motion looks like, okay? And now it's kind of cool to look at what will different integrators give you. Okay, let's try it like this. Copy. So what do you think forward Euler will give you for the time step of 0.4 seconds? It's actually kind of cool. I need to find a better way of looking up the files. Forward Euler. That's what it gives you, okay? So that kind of, the scale is something like this, okay? But the idea is kind of clear. You can kind of see the overshooting, right? And that's one step, right? Then that integrator gets applied again on the output of the previous integration step, okay?
Just one thing I want to point out, the circles are Hamiltonian level sets there.
Right. Yeah, I didn't explain that. What are these ovals here? Those are the level sets of the Hamiltonian, okay? So that means that the H, what is a level set? H, switch this off. Level set means that H, X, and V equals some constant. I think here the constant was 0.41. There was a different, do you remember, Jink, what it was here? So some different constant, that doesn't really matter. So those are the level sets of the Hamiltonian, okay? Oh yeah, and that's what you want to, you can go ahead and say it.
Right, so if you look at the exact solution,
Yep.
That's exactly what energy conservation is.
This oval here is exactly the same as this oval here. All of the ovals here are exactly the same as all the ovals
Points
there.
that are on a level set will only move along that level set, and that's why we have them drawn here.
Meaning if you, exactly, thanks. So if you have a point here, that point can only move somewhere on the same oval. It cannot go anywhere else. Otherwise, it would violate energy conservation.
So what was the method used for the sort of the exemplar, the best example? Is that exact? Exact solution?
Mhm.
Okay.
No. Is that what you're talking about?
This
Yeah,
one? This
yeah.
one right here?
Yeah.
Which method did we use?
Yeah.
We just used symplectic Euler with super tiniest time step.
Oh, okay.
At this point, it doesn't actually matter what method you use because they all converge. As you decrease the time step more and more, actually any integration method with really small time step would give you exactly the solution.
Okay. Yeah, we did discuss that last week. I was just curious.
No, that's a good question. Yep.
Okay.
But what we want to do, what we would want to have a good numerical integrator should be able to approximate this with relatively large time step, right? Because if you don't want to be spending, that was kind of slow, right? To do like 10,000 time steps. Ideally, you would do just one and you would just get it. Yeah. So the forward Euler is absolutely terrible, and here you can kind of see why. Okay. So this was forward Euler.
And that's because the errors can accumulate over time steps.
No, this is even just one time step. This is because the time step is relatively large.
Oh,
If the time step was relatively small, you couldn't see the difference. Okay, that's why I also chose the parameters like this, and that's why I also put the 128 here. Okay, so you can actually see. It's kind of probably exaggerated, right? Probably you would be using smaller time steps, so it's like.
You are right that the next time step would be using that as a
Worse.
base and getting more.
Like one time step like maps this point like over here, right? So this point like goes there, right? But then the next point, like you can imagine it goes back, right? And the next point is like over there, and then it shoots like somewhere far away, and eventually it flies off the screen, right? Actually pretty quickly, right? You can see how this is like inflating, right? Yep.
So the warping of the level sets, does it? Like, I mean, it shows that energy is not getting conserved.
Correct.
What is the warping of the image representing?
That's a great question. Symplecticity, basically, or the area preservation. So this all these, and that's why Gene created these little animals. They all have the same area, right? And that area should be preserved if the integrator is symplectic. Okay, here you can clearly see that this fish is much bigger than it was, so it's also not a symplectic integrator. Okay. So if you look instead at backward Euler, this. Delete. Oh yeah. Come on. Just do this. So backward Euler. How do you think it will look like? That's
Yeah, kinda condensed inward.
squished. Yeah, squished is right. This is how backward Euler looks like. Oh, I even had it labeled there, and it's probably a little bit smaller. It's probably something like this. Okay, you can tell where the axes are, right? The axes are always, it always has to pass through this point. That's the one thing, the origin, this thing here always needs to be mapped to the same point, right? Because if the positions of velocity is 0, it's not going anywhere. So the origin is fixed. So this is what backward Euler does. And it's actually like the opposite of forward Euler, right? That's an opposite problem. Instead of overshooting the total energy, it's actually undershooting it. So it's like you can see it's contracting everything. Okay. You can also visually see that symplecticity is also violated in a different way. Now all these fishes far away are getting smaller. The area should have been preserved. And it is preserved in this exact solution, right? This can be squished, the octopus, but if you measure the area of this entire deformed box or square, then it's the same as the area of the box in the initial conditions. That's the symplecticity property. Okay, it's also violated by backward or implicit Euler, but in a different direction than forward Euler. And that's actually not a coincidence because these methods are actually tightly related, the forward and backward Euler. Let me actually explain you how, because it's kind of cool. If you let's think about this experiment. Let's do first step of backward Euler, and second we will do a step of forward Euler, but going backwards in time. Okay, so with time step minus h. Okay, it's actually kind of easy to compute what that will do, interestingly, even though backward Euler is not always easy to evaluate. So what backward Euler does, it does xk plus 1 is xk plus hvk plus 1, right? And the velocity update rule is vk plus hf of xk plus 1. So that means that xk, vk were my initial conditions. I computed the backward Euler update rule, xk plus 1, vk plus 1. And then the second thing I do the forward Euler with minus h. Okay, so that means that I compute some xk plus 2, which starts at xk plus 1, and then does update minus h, because I said the time step is going to be minus h, vk plus 1. Okay, that's a forward Euler update rule. And vk plus 2 similarly will be vk plus 1 minus h f of xk plus 1. Okay, and do you see the funny thing that happens there? Just with algebra, what this thing is and what this thing is.
Wouldn't it be xk and vk?
Exactly, Brian. Exactly. It's exactly xk and vk. So that's the funny thing. If you take a step of backward Euler, and after that you take a step of forward Euler with minus h, you get back where you started. Okay, so you can see that these methods are kind of complementary to each other. I think some people will time adjoint dual or yeah, something like this. Yeah. That also explains why the images look kind of similar, except that they are opposite. So this, so the backward Euler does not produce the explosions forward Euler does. It has a different artifact. Did you guys talk about it last week? Damping, yes. And that's a numerical damping. That's an artificial damping, because you can see that the energy is actually getting lost. Okay, again, energy should have been conserved, right? The ovals should map to the same ovals. Okay, with forward Euler, these ovals are getting distorted into some bigger curves, and with backward Euler, they are actually getting contracted. They are getting smaller. Okay, and this is known as numerical dissipation or numerical damping, and that means that if you keep running backward Euler over and over again, you have the opposite problem of forward Euler. Forward Euler was exploding the energy out of the window. This will be sucking the energy away from the system, even if the system was supposed to be conserving it. So eventually it will all stop. Okay? So neither of these methods, forward or backward Euler, is very useful if you want to simulate something for a long period of time. Like people do use this like in astrophysics. Imagine you simulate some planets orbiting around for millions of years, right? If there are these biases that energy is getting decreased or increased, then it's no good because the long-time predictions are going to be useless. Forward Euler will just shoot up somewhere completely away from the continuous solution. Backward Euler will just say that everything will stop eventually at some random point. Okay? And that's also why symplecticity is such an important property. The simplest symplectic algorithm is a symplectic Euler. And it's kind of cool that the symplectic Euler is just a small modification of the forward and backward one. Did you guys have that the last week? So what is the rules for a symplectic Euler? It's kind of like a combination of the forward and backward in a funny way, which is actually very fundamental. So if anybody remembers that, how is the update rule for symplectic Euler? So I go implicit on positions, okay? So I do basically implicit Euler step on positions. So I use the vk plus 1 when I'm writing positions, x's, okay? So basically implicit update. But the trick is that the velocities I update explicitly. Okay, so this is an explicit step. Okay, if you had forward Euler, you would have here vk. If you had implicit Euler, you would have here xk plus 1. Symplectic Euler is kind of blend of them. It's one way you can look at it. Okay, and it's actually really cool because you can evaluate it like this. You can evaluate this first. You know what is vk, you know what is xk. You can compute f of xk. You can compute vk plus 1. Once you have computed vk plus 1, you use it here, right? So you also computed xk plus 1. So this actually is an explicit method. Much easier to solve than implicit methods, much easier, okay? And indeed, it is symplectic, okay? I won't have the time to do it today, but you can actually prove it. You can prove this for your voluntary homework. You can do exactly this. You can compute the Jacobian of the symplectic Euler, and after like a little bit of algebra, you will see that this actually is true, okay? And graphically, what that means is this. So let me compare, do a similar image here. Oops. So initial conditions, and let me show you, how do you think that will look like? Symplectic Euler, there we go. So that's what it did. Again, you can imagine that this is the origin, right? It has to go through it. So this is what the symplectic Euler does. So you can notice that the areas indeed look like they are conserved. Okay, that's we discussed this before, that the key property of simplicity is actually conserving the areas, just like the ground truth solution, right? This is the accurate solution. So the areas of each of the small animal figures were preserved. Guess what? They are preserved here too. Okay, there might be a lot of distortion. You can preserve area with ton of distortion, and that's kind of what is happening here. Like, look at this fish, right? Like, that got like squished like crazy, but the area actually still adds up. Okay, so it's still the same area as of this poor fish over there. Okay, and that's the hallmark of symplecticity. And actually, it turns out that the symplectic Euler has a beautiful property. It does not have this consistent bias of overshooting or undershooting the energy. But at least with a small enough time step, the energy oscillates about the right value. Okay, it certainly does not conserve the energy, right? You can see that the ovals were distorted in a funny way, and this is not obvious at all how to prove this, but the energy actually behaves much better. It does not have this consistent bias of forward or backward Euler. Okay, and that's why the symplectic methods are so important. And if you talk to somebody like in molecular dynamics or something, that's what they would be using, some symplectic integrator, because they want to simulate over lots of time steps. So that's what is a good method to use. And there is more to it, but we will continue next week, I guess. Any burning questions? Looks like the recording survived, so that's good. Stop it here. Or do you have any more questions? I think we need to end now.